Okay, so with that, I would like to pass over to
Hello.
Michela Morente, who's the Executive Secretary of GBEP.
Thank you. Thank you very much. I would like to welcome you all to this GBEP e-learning webinar on the BiogasDoneRight. So we will hear a presentation on the BiogasDoneRight, which is a model for agricultural biogas based on the use of feedstocks that do not compete with food or fodder crops. For those of you who doesn't know the Global Bioenergy Partnership, the Global Bioenergy Partnership is an international initiative which brings together approximately 80 between partners and observers among governments, international organizations, research institutes, and relevant stakeholders in the field of bioenergy. And one of the main aim of the partnership is to facilitate dialogue and discussions, exchange of lessons learned in order to promote a sustainable development of bioenergy. This e-learning webinar has been organized in the context of an activity group on biogas, which has been established in GBEP, and in particular within the context of the working group on capacity building. I would like to present our presenter today is Professor Bruce Dale. He's from the Michigan State University. He's chemical engineer and he's professor at the Michigan State University of Chemical Engineering. He serves as editor of in many contexts, and also he received and he won a couple of awards for his contribution to biofuel production and to agriculture. And he has always published over 300 archival journal papers and other relevant articles on the bioenergy and on renewable related matters. Join me in thanking Professor Bruce Dale for his availability, and I would like to give the floor now to Professor Bruce Dale for his presentation of the BiogasDoneRight model.
Thank you,
Bruce,
Michaela.
The floor is yours.
Okay, thank you, Michaela. Thank you, Connie. It's a pleasure to be with you this morning, even though I can't see anyone. I'm going to give an English version of a presentation done by my friend Jorge Hilbert from the Institute of Rural Engineering in Argentina. Jorge encouraged me to add my own perspectives here, and so I will do that, but since our time is limited, I will talk fast and try to hit some high points. The focus here, of course, is bioenergy, but I'm increasingly of the opinion that people who are practicing bioenergy or thinking about it are not giving enough thought to the agriculture that underlies or underpins sustainable bioenergy. The fact is, we'll never have sustainable bioenergy unless we have a stable agricultural system that underlies it. And one of the particular points this I think is just not appreciated enough is this idea that, in fact, agriculture as it's practiced over a lot of the globe today is simply not sustainable. And it's not sustainable in many levels, but let me focus first on the low income levels of farmers. We can't expect agriculture and farmers to change their practices significantly, many of which practices are not sustainable, unless they can get higher levels of income. Who can expect an industry to change without enough capital flow to make those changes? So the things that we're concerned about, the weed resistance, the soil nutrition, organic matter, fertilizer costs, all the pollution, also have their center in the fact that farmers simply don't make enough money to make their changes. They're debt slaves, they're debt trapped like many of the rest of us are. So one way of viewing this system is that we have what we would call bioenergy enabled sustainable agriculture along the lines of the Sustainable Development Goals. Many of these goals are met by bioenergy, by sustainable bioenergy, and we'll just try to discuss those as we go. Again, we don't have a lot of time, so I'll talk fast and try to hit the high points. Jorge points out correctly that there are huge and multiple complex interactions. These are just, frankly, have not been known before. And so we have the biofuels and bioproducts international rules, food patterns, ag patterns, all these things with very great deal of interactions and unknown that we've had before. And we're trying to develop or build this in terms of a sustainable bioeconomy. Okay, so and this is in the context of thinking about biorefineries. A biorefinery acts to add value to the plant material that's processed. That's its fundamental objective here, and it has to add enough value so that that all the costs are met and a profit remains. That's, again, seems obvious, but we're I think don't pay enough attention to the fact that all the pieces have to work together here. So all the way from biofuels to bioenergy. And what I want to, again, focus on today, bioenergy done correctly allows us to develop a more sustainable agricultural sector by providing both the income and also the raw materials and the outputs that would help us move in that direction of a more sustainable agriculture. I don't believe it's going to be possible to have a sustainable society without sustainable agriculture at its base, and bioenergy provides one of our few vehicles for allowing that to happen. At the heart of the biogas done right, or this sustainable energy, is flexible crops. Crops that are multi-purpose, that could be used for a variety of purposes, including fuels and food and energy, and the environmental services we wish them to provide. So then what we would call an agricultural residue, and some people call it a waste, but it's just a residue, can become a resource or potential source of resources we want to reduce and prevent, but then there's finally still some material that's going to have to be disposed of. And all these principles are met in what we call biogas done right. The conversion technology is key here. How do we convert these residues into a resource? And we believe an important key here is bioenergy. The bioenergy constitutes a starting point or a link or a basis or a catalyst, depending however you wish to phrase it, toward a circular economy that's linked to the bioeconomy. And I would say based in agriculture too. We're emphasizing agriculture rather than silviculture at the moment, but the principles apply there. Okay, so what happens is that bioenergy becomes a key piece of a linked system. It's an essential part of a linked system that provides environmental services, food, and fuel. Okay. So now we're at the main point of the presentation, where we'll spend the remaining 40 minutes or so of my presentation. Biogas done right allows us to simultaneously improve water quality, reduce erosion, reduce greenhouse gases, very importantly, increase the income flow to farmers, and reduce their volatility of food, feed, and energy markets by having multiple uses for a single agricultural material. You can arbitrage or choose between food and energy products. So there'll be emission credits. The risk of indirect land use change is reduced. I think it's eliminated, but it's certainly reduced. And that much better water use, reduce the loss of nutrients. So all these things can occur in an intelligently organized biogas done right system. Boy. My PowerPoint has decided to take a vacation. Let me go ahead and say what's on the next slide so we can go through it more quickly. The features of biogas done right, or biogas fatto bene as our Italian friends call it, includes these main features, and the impacts or the effects of the features. I'm having trouble having my PowerPoint. Apparently it's just not cooperating this morning. I'm sorry. We'll keep moving, and I'll try to do the best I can. I'm sorry. PowerPoint has crashed on me. That's not happened to me before. Let's see if I can get it back. Okay, go through this quickly and try to catch up with where we were. Okay, so this is the idea of a biogas biorefinery, all of it based in the anaerobic digestion plant where the biomass is input. And we have a variety of products and energy products, plastic products, fertilizers, not all of which have to be done at one spot at any one time. But the point is to add enough value to the incoming nutrients, incoming materials, that your costs are more than met. A simplified version, and I think a useful version is shown here. This simply shows that what biogas done right is to take animal waste and a variety of both principal and double crops, feed them into the anaerobic digester system, which produces electricity to the grid and or biomethane to the grid, while still providing the food and the animal products that we're currently accustomed to getting from agriculture. There are two key technologies that are used here. Anaerobic digestion, which is well known and widely used, and double cropping, which is also widely known and well used. What we propose is that they be integrated. This is actually the heart of biogas done right. Okay, so if we use continuous crop cover and integrate our crops throughout the year, we can increase the number of days throughout the year that we capture photosynthesis. This is in contrast to much traditional agriculture in which no photosynthesis is captured during many months. Here are two different crop rotations that are actually practiced by our Italian colleagues using biogas done right. There is the conventional wheat and tomato, where you grow wheat, then bare ground, then tomato, then wheat again, and then bare ground. In biogas done right, wheat and tomato production are combined with sequential cropping. Wheat grain, followed by two silage crops of maize and triticale, tomato and wheat again, and then the maize silage. And importantly, the blue dots here represent when the digestate, the residue from anaerobic digestion, is applied much more in harmony with the plant demands. So there's less likelihood of erosion or other problems and nutrient loss. Okay, I'm going to go past this one kind of quickly. The Ecofis is an environmental consulting group, and they reviewed the biomass production of two large Italian fields. These are practicing bioenergy using biogas done right. What they noted was that instead of yields decreasing, the yields of traditional crops are actually increasing. This is to be expected, actually, because the organic matter is increasing and there's a recycle of nutrients that goes on. So instead of having an indirect land use change causing decrease in food production with bioenergy, we actually have increased crop yields while also harvesting bioenergy under essentially the same conditions. There is a negative indirect land use change. There is an increase in the food and feed potential because of bioenergy being integrated with agriculture. Okay. The Italians have also noticed very positive impacts on soil quality. There's a substantial increase of organic carbon. There is diminished erosion, a probable increase in biological activity. Soil compaction is reduced because they apply the digestate by plyclines, and additional nutrient or soil nutrition is being suggested here. So in a lot of the world, or there's a concern about the double cropping or continuous cropping, drawing down water tables, and that's viewed in some places as being perhaps a negative. However, in Argentina and many other places, change in rainfall patterns are actually causing the water table to rise and will cause flooding of agricultural land. With the use of the double cropping, it could increase the value of these lands by reducing the excess water that's is being observed. So we have to think very locally but systemically at the same time about bioenergy. When digestate is carefully applied using required knowledge and technology, as it is under biogas done right, the It's a great improvement over current practices for spreading manure. Manure practicing leads to loss of nutrients, especially nitrogen, and results in contamination and a lot of social resistance. But when our Italian friends and others who practice these biogas done right principles apply the nutrient, the loss of nitrogen and other volatiles is essentially eliminated. With digestate recycle, the soil organic matter also is improving. These are small, but they continue to be measured, and they're scientifically, statistically valid. So from 2013 to 2016, in a number of the individual farms or fields of the Palazetto farm, we see increased soil organic matter. In other words, increased soil fertility. I'm going to go back and view that for just a moment again. This is farmers practice these principles now for about the last 7 years, and it's been tracking organic matter over the last 4 years. So there are significant increases. Also, in terms of the cost of biomass production, the results are what you might expect. The incorporation of the sequential crops increases silage yield by more than half. Labor costs increase, but the land opportunity cost is unchanged. And importantly, the cost of fertilizers is essentially zero. This is because the phosphorus and the potassium were almost 100% recycled, and the nitrogen is about 60% recycled through the digestate. So it's a great improvement over the cost of production of the biomass. It's about the cost per unit energy is reduced by about 40%, and per feed unit by about 20%. The farmer income per hectare is increased by around 40%, a very significant increase. Again, the land is the farmer's principal capital asset, and making better use of that makes the whole system more sustainable from the farmer's point of view. Unless for the farmer the system is more sustainable, it can't be more sustainable for society. The farmers won't practice it unless it works better for them. Okay. So to briefly summarize, the journal that I edit, have the privilege of editing, published the 4 case studies using biogas done right in Italy, and this is the citation of that paper. Here is one of the main tables or figures from the paper. These are of actual farms and actual digesters operating under different configurations. The reference or base case was a 1 megawatt digester system that operates under the German model, which feeds the digester with maize silage growing on 285 hectares. This is conventional. This is so-called conventional biogas production. Okay. The remaining 3 cases were different biogas done right configurations that were operating with different proportions of primary and double crops grown for the digester, also crop residues, and also manure. So this just shows the first and second culture, and also the co-products, as well as the byproducts in maize. So there are 4 different cases. One is the more or less traditional maize silage, and there are other here 3 different cases that represent biogas done right. This is not biogas done right. These 3, however, practice biogas done right. Okay, so biogas done right system leads to increased greenhouse gas emissions in some categories, but greatly decreased emissions in other categories. Emissions do increase for crop cultivation and transport for conversion and storage of the digestate, but emissions greatly decrease from the storage of residues and effluents, the reduced requirement for fossil fertilizers, and the capture of sorbent in the soils. And we have detailed these factors again for these 4 cases. Once again, this represents the conventional biogas production, and here's the carbon footprint in grams of CO2 per equivalent per megajoule for corn silage base. This is crop residues and manures. And this is the main crop with crop residues, and these are byproducts. So you go from a reduced but nonetheless significant carbon footprint to very low to even negative, depending on how much manure or byproducts you can use of the carbon footprint. So here is another slide way of viewing that. in terms of the sustainability analysis. Once again, grams of CO2 per megajoule. And here it is for fossil fuels in the European Union, the average and then the marginal fossil fuel at about 115 grams of CO2 per megajoule. Conventional biogas achieves 34, with the 3 BiogasDoneRight configurations increase almost zero to negative overall carbon emissions. Okay. So there is it's hard to overestimate, sorry, I'll go back here. It's hard to overestimate the importance of this. Here is a way of actually practicing bioenergy in a way that enhances agricultural productivity, increases farmer income, and gives a very low carbon footprint fuel, a flexible fuel like biogas or to make electricity from, but which can be upgraded to biomethane, which is a new opportunity that's now being more exploited by our friends in Italy. Biogas contains about 55% biomethane, and you can upgrade biogas to biomethane with a, sorry, I'm going back again, biogas to biomethane using well-developed technology. It's then equivalent to natural gas and can be injected in the grid, and you can use it in any application where conventional fossil methane is used. This is not an advantage that's enjoyed by any other biofuel that I'm aware of. Ethanol doesn't have this advantage in most of the world because the engines and the transport systems are designed for gasoline and diesel. But biogas, once it's converted into biomethane, is that kind of flexible product and widely accepted. I'm going to skip this, but this is the vision for biomethane in France, how they think it might change. And again, biomethane is obtained by removing carbon dioxide and other impurities from biogas. It is then identical to biomethane or to conventional fossil gas and can be used in all the same pipelines without any infrastructure changes, without any of the attendant expenses that go with that infrastructure changes. What's compared here is the distance traveled per hectare of cultivated land for several different biofuels, including biomethane. This is biogas to gasification, and biodiesel and bioethanol. And there's a substantial increase here in the miles traveled per hectare of cultivated land. Okay. So one of the principal values, and it's a paper now that I'm working on with my Italian colleagues and with Jorge to write, is how you might use biomethane, a very low carbon sustainable fuel, but one that's dispatchable, can be dispatched whenever it's needed, to balance out the demand patterns for intermittent or variable sources like wind or solar. Provide the biomethane to balance out the role of renewable energies when solar and wind are not available. The natural gas grids have a huge buffer capacity that is there and is available at low cost, whereas for solar and wind you would have to build out a huge battery storage or other types of storage capacity. So it's and biomethane, natural gas, has already been designed to deal with temporal variations, whereas the electricity system is not. Okay. Again, the removal of carbon dioxide from biogas in order to produce biomethane is a well-known technology. We don't have to wait for new technologies to be developed. And there are various approaches. The main need is to remove carbon dioxide, and there are a variety of purification technologies available to do that. The specific costs here in investment costs in euros per normal cubic meter per hour generally even out and become the same at high capacity, but in lower volume systems, lower throughput systems, there are significant differences between the different approaches, including water scrubbing, amine scrubbing, and membranes. Okay, it's very interesting. But once again, it's available technology. An interesting vision here that I think really needs to be explored is the idea of an energy independent farm. If agriculture is our most basic human activity, economic activity, and I believe it is, then making it independent, making agriculture independent or much less dependent on fossil energy is very important. And of course, agriculture as currently practiced is fossil energy dependent. There's just no getting around it. So by using the biogas to produce biomethane, you can run farm implements. By recycling most of the nitrogen and all the phosphorus and potassium, remove that fossil fuel dependence. By taking some of the methane to produce ammonia, which is the current of way ammonia is made, then you get the opportunity for the farm to be essentially energy independent. This is really important as far as I'm concerned. Okay, so now some real field examples. These are practical examples and demonstrate different features of the biogas biomethane systems that we've already talked about briefly. Okay, this is the first one is the agricultural cooperative La Torre in Italy. It has a cattle population of a maximum of about 10,000, minimum 2,500, 2 animal cycles of animal feeding, and this is the animal feed coming in their final weights. It's hooked up also to a photovoltaic 1 megawatt plant. So a 1 megawatt plant is part of this, and there are 2 1 megawatt biogas plants. The final products include animals for consumption, digestate, and electricity. This is an aerial view of the cooperative with its covered stables right here, the 2 biogas plants, and the photovoltaic panels. That's enough for that. Engineers, chemical engineers and others tend to focus on, myself, for example, my colleagues tend to focus on conversion processes. But we know actually for a large-scale system, the key is logistics. How do you move stuff around? And that has been an issue that I think has not been sufficiently addressed in most bioenergy systems today. It is addressed in Biogas Done Right. It's important, but all the logistics essentially are confined to the farm. Instead of hauling biomass over many, many miles, essentially all of the biomass and all logistics are internal logistics. Okay, it's a very important thing. It's absolutely fundamental, as Jorge correctly points out. And the logistics are simply not paid enough attention to in current discussions of conversion technology. Hopefully that will become less important. Excuse me while I take a sip of water. I'm speaking from Salt Lake City, Utah, where the air is very dry. Okay, so the equipment used here is modern, it's high capacity and powerful. The digestate is transferred very rapidly from the holding pond to the tank here on this truck. And then there's the issue of intelligently applying the digestate to the field. Manure spreading, of course, is widely practiced, but it's frankly not very intelligent, and it tends to make bad neighbors. Your neighbors get upset with you. So when the digestate is spread by this umbilical cord approach, the soil compaction is avoided. And okay, we have a picture. Okay, I triggered the picture, the movie actually. So I guess I'll go ahead and do that. Let's see if I can do that again. This is how it works. Dragging along this umbilical cord, that's how the digestate is applied. It's really a very interesting and very impressive system. Okay, go on to the next then. This reduces soil compaction, as said, and the flexibility. The system is highly flexible. Once again, the digesters are fed in a professional, intelligent way. It is absolutely critical to design the digesters and the operation here to accept a variety of feedstocks. If you're going to allow diversity in agriculture to increase the sustainability, then you must accommodate that diversity of agricultural sources into your processing system. In other words, the sustainability of the agricultural part of the system has to be recognized in the design of all the downstream systems, everything with which the system copes later on. Okay, So again, it's a highly professional, highly controlled operation. The system is monitored. Their management, the sedimentation in the biogas digester, and it requires actually quite a high level of professional advancement. So this is sustainable also in terms of increasing the general education level and pay level of the people who operate the biogas plant. They become actually quite sophisticated and are able to be paid good wages because of the talents they have. Here is the second case. This is the Sociedad Agricola Casola Francesco Luigini. How'd you like that? Okay, this is the Agricola Casola system. The first plant, it was built in 2 stages. The first plant had about 4.6 million euros of biogas, feeding a lot of dairy cows. The second plant, sorry, the timer, I don't know how to change the timer setting quickly, so I'm just going to reverse it when needed. The second biogas plant was added in 2012 to allow for pre-hydrolysis and less storage. And the initial storage of biomass is done right here. It's evolved to produce different products. So they feed 250 dairy animals. The actual average milk production about 68 liters per day. The animal bedding is pasteurized, and it's pasteurized digestate. In other words, it comes from the system. They produce concentrated liquid fertilizers, controlled dried air, bales of feed, a forage drying service that they sell to their neighbors, and 2 biogas plants from electricity. I mentioned the importance of providing additional income for farmers. They went from a cash flow of 600,000 euros. They went from a cash flow of 600,000 euros per year to a cash flow of 12 million euros per year. It's absolutely critical that farmers be able to generate more income if we want more sustainable agriculture. I'm going to repeat this several more times. I hope that you take away, at least from this presentation, the idea that farming has to become more economically sustainable before it will become more environmentally sustainable, and the energy products produced by Biogas Done Right allow that to happen. They would not happen. The energy, and I should say other products like animal bedding and digestate, is what's possible because of Biogas Done Right. It would not happen otherwise. Okay, now we'll go ahead with this other slide. Here's the different feedstock sources, a wide variety of different feedstocks that are used to feed the plant. Silage, straw, residues, manures, and so forth. And these can be changed as needed. Wastes include bedding from rabbits, milk cattle. They're stored in large concrete bunkers, and each of them has their own distinct feed properties as well as how they're fed to the system and their biogas property. If the biodigesters fail, if they're not properly fed, they can fail, greatly increasing the cost of production. Once again, the need for very intelligent and sophisticated management here. Okay. So I come back to the importance of logistics, and as Jorge points out, the feeding and the digestate logistics, this is done just in time, as needed to the digesters. And the key problems that are encountered in digesters are from the physical and rheological properties of materials. They have sedimentation and crust formation. And that requires using the settling tanks to remove inerts, mixing and homogenizing tanks, continuous mechanical feeding, a variety of positive measures taken, management to make sure the digesters don't fail, and as well as secondary digesters. Okay. So here are some of the products of the system. Again, the generator produces electricity, but the generator also provides a 40% or 45% efficient generator, provides a lot of waste heat that is actually used here in this system to dry bales of animal feed in these very interesting bale dryers. It's used to evaporate and produce concentrated liquid fertilizers from the residues of the digestate, and on and on and on, as well as to pasteurize the the bedding, which also leads, in other words, the bedding of the animals is pasteurized or heat treated. That enables a 50% reduction in the amount of antibiotics required to keep the animals healthy. So all these system level benefits that may not appear at first happen because of the system integration and the waste heat that's available. Here is the picture, for example, of the pasteurized cellulosic bed material and the investment that was required to get there. These are the dried round bales of animal feed that are stored under roof that can either used on the farm or can be sold to the farmers' neighbors. They're locally, they're commercial products. Here's a picture, for example, of the concentrated liquid fertilizers that are generated by evaporating a portion of the liquid from the digestate and how these are taken away. A variable rate fertilization machinery. It's really a very sophisticated operation. I mentioned before a key feature of the biogas done right is the fertilization of nearby fields with digestate. It's critical to be able to use your digestate on the farmer's fields or very close by. You can't afford to haul it around. But the closing the loop by applying digestate to the field allows you to recycle the nutrients and recycle stabilized organic matter, increasing the field fertility. To do this without digestate recycle is not biogas done right. In other words, if you are not using the digestate in this way, you're not intelligently applying the principles of biogas done right. The Italians actually do this using green index satellite monitoring and field-specific maps. These are all technologies that are relatively inexpensive and within the reach of farmers in a lot of different places, but aren't used because this link here with agriculture has not been made. In other words, the link between energy production and agriculture has not been made enough in bioenergy systems. So that's another message that I hope you'll take away from this presentation. We have to start thinking about agriculture and bioenergy as linked systems, both of which depend on the other to become sustainable. Okay, so we have to think about the whole system, which is part of Jorge's title, a systemic view. By the way, again, when you spread your digestate in this way, the odor problems are essentially eliminated, and so your neighbors don't object to you farming, as well as the nitrogen balance is being really improved. Okay, now switching from Italy to some studies that were done recently in Argentina that Jorge supervised as part of his work. And I see that I'm going to get done with my presentation actually a bit early, so we'll have more time for talking. I hurried too much, but it'll be good to have a good conversation. So these are results of environmental studies in real plants in Argentina during 2016 and 2017. The studies focused both on the energy return on investment and the water use and carbon footprints. Okay, so how much water is used, how much carbon is used, and what's the energy return on energy invested. Okay. For comparison, here is the total energy consumption of a conventional biogas plant. About 78%, almost 80% of the total energy required to run the farm is in crop production. Largely this is diesel for field operations as well as the fertilizer, primarily again nitrogen fertilizer, very intensive, energy intensive system. That's why the nitrogen recycle made possible by biogas done right is so important. Transporting the silage and digestate, and the bioelectric plant consumes about 8%, actually 8% of the electricity plant. So this is where about 80% is in the agricultural phase, and then 14% for transport, 8% for conversion. With respect to the electricity in the Argentine national electric grid, these are the actual achieved reductions versus electricity in the grid in 2015. There's an 83% reduction in the theoretical total energy produced by the plant. The electric energy delivered by the plant reduces the reduces emissions by about 50%, and the total delivered energy. In other words, you have your choice here of what energy you choose. The theoretical total energy produced by the plant, the thermal energy delivered by the plant, the electric energy delivered by the plant, and the total delivered energy. So you have to choose the basis. And just to be very clear, Jorge has done this, Jorge and his coworkers have done this very carefully and very correctly. They've chosen 4 different bases, and they make the comparison on all 4. Depending on what your plant actually allows you to do, whether you're simply delivering electric energy or thermal energy or both, and versus the theoretical possible. Okay, so sorry for again having to stop the timer and move backward. But these are the emissions factors that are achieved according to the energy used, and they're very significant. I'm not going to go through these in a lot of detail. I think it will be more interesting and more valuable to have a conversation after my presentation, which has only got a few more slides to go. But the reference values are those used here by the Clean Development Mechanism, which is created by the United Nations. So for those of us that may not be fluent in Spanish, from top to bottom, there's 13.7 million kilowatt hours per year of electrical and thermal energy that are exploited by the plant. Here, 7.8 million kilowatt hours per year of electricity sold to the grid. So this is electricity and thermal energy actually generated by the plant. And row 3 here, is 4.1 million cubic meters of normal cubic meters of biogas produced per year by the plant. And so then a variety of other measures here that may be of interest to you. They'll all be part of the presentation that's made available. Okay, so this is the actual analysis of the plant energy return rate. Electrical energy sold to the grid is about 46,000 gigajoules. Thermal energy developed to the bioenergy plant, 21 or so. The total energy, therefore, that is sold is on the order of 68.2 gigajoules. The energy return on an investment is about 3.7, and if it's only thermal energy, around 2.5. And there are many ways of increasing these values that Jorge and his team are focusing on now. So let me kind of wrap up things here. This is a slide from a year ago taken at the annual meeting of the Italian Biogas Consortium. This is your presenter here with the microphone and the hat. And here's our friend Jorge over here as we're presenting this before the biogas meeting. This is called the International Working Group on Biogas. And it's this group that's currently putting together a paper that it's ready to be submitted now for review that we hope will show some of the international potential of biogas done right. Biogas done right in this way provides a new and expanded opportunity for application of anaerobic digestion, as well as a new and expanded opportunity for the application of sequential cropping with all of its attendant benefits for the agricultural system. When the anaerobic digestion is combined with sequential cropping, it's combined with digestate recycle, you get these enormous systemic environmental and economic benefits that will greatly improve both the economic and environmental performance of agriculture. Okay, these strategic considerations, again, we've talked about soil nutritional benefits, soil nutritional deficits, largely addressed by nutrient recycle, the phosphorus and potassium in the digestate. Groundwater pollution is greatly reduced because you're not applying excess phosphorus and potassium. Those are captured and reused. Gaseous emissions are greatly reduced by manure use in the system, and also less application of volatile nitrogen to the fields. And once again, a key here, the poor profitability of many agricultural activities Intelligent application of biogas done right, taking advantage of all of its properties, requires us to be focused, locally oriented, and context specific in terms of infrastructure, local conditions, while keeping in mind global markets. Okay, so Biogas Done Right platform opens a new opportunity for biogas systems. It's got strategic importance for farms, from economic, energy, and environmental perspectives. Helps resolve critical problems such as soil nutrition deficits, contamination of various kinds, gaseous and water emissions, energy deficiencies, and especially low farmer income. There are very huge areas of globe where agriculture is being practiced, where these principles could be applied, and again, taking into account the context and available infrastructure. And this is what excuse me, I have to take a sip of water every now and then. There are huge areas throughout the world where these principles could be applied, adapting the system to what is required by both the agricultural needs, the energy needs, and the environmental needs of a particular system. We have to think systemically. We have to think in terms of the agriculture as a part of bioenergy that unless we can practice agriculture sustainably, there will be no such thing as sustainable bioenergy or a bioeconomy built on the products of agriculture that's not sustainable. Okay, so thanks very much. According to my clock here, we have 15 or so minutes for a discussion. I'd be happy to do that and entertain questions. So again, thank you very much for listening.
Bruce, thank you so much for the presentation. It's a fantastic overview of the Biogas Done Right system, and I'm sure that there will be lots of questions. So I'm just going to activate everybody's microphones. You now all have microphone rights, but I would just ask that you mute your microphones. You can do that in the top bar at the top of the screen until you would like to ask a question. You can also raise your hand and then we'll know that you have a particular question. Or if you'd prefer, instead of asking the question, you can also write it in the chat. And I'm sure that Bruce will be able to see that as well and answer those questions. So, as I said, a fantastic presentation there, Bruce, and it was really interesting to see all of the positive aspects that this model, the Biogas Done Right model, can have. But I just wanted, just to start the discussion, I guess, I wondered whether you would touch on some of the potential challenges of adapting this system in other regions of the world. You mentioned specifically Italy and Argentina as two places where this system has been proven to work very well. But I wondered, in terms of other regions, what may be some of, whether you touch on some of the potential challenges.
Thank you. I think there are two issues here. One is where what you might call conventional monocropping, highly mechanized agriculture is already being practiced, and that's practiced again through Italy, through most of the European Union, throughout essentially all of the United States and all of Argentina. So those are areas where it can be applied, I think, essentially as is, and that is what the paper that I mentioned, that's what we're focusing on, is the potential for expanding it in those areas. In those areas, what would be necessary to apply Biogas Done Right was what was necessary in Italy, and that is an incentive to produce the bioenergy that allowed the farmers to get the capital investment required to install the biogas plants. If there is an incentive, some sort of way to help the farmers get the money together, the capital required to institute these Biogas Done Right plants, then that's exactly what happened in Italy. It grew, biogas grew with a doubling time, or bioenergy grew with a doubling time that was truly exponential. I mean real exponential growth, a doubling time of 14 months. That is the most rapid application or growth of bioenergy that I'm aware of throughout the entire world. So that's one area. In other words, where more or less conventional monocropping, machinery-intensive agriculture is already practiced. The Italian farmers that lead this group are a very adventurous and intellectually oriented group. They're very innovative, and what they're doing now also is to explore the potential for biogas done right in arid and semi-arid areas that would be applicable to a lot of Italy, for instance, Sicily, and also North Africa, where it would be based more on cactus or opuntia species generally, where the areas are not farmed and only very lightly grazed, where you could grow these essentially CAM, these are crassulacetic acid metabolism plants, but they're plants that are very water efficient, and use them as the basis for the biogas plant. We'll see how that works out. The studies are ongoing, but I'm very excited by that potential. A lot of rural poverty is based on lack of access to energy. And if you could grow sustainable plants in dry, arid areas where the poverty rates are very high, in a way that would allow you to improve agriculture by recycling the digestate and make good and have some energy left over, the biogas, the electricity, then I think you fundamentally change places for better. Okay, so that was a long answer. I'll try to do.
No, thank you very much, Bruce. That was a really clear explanation of what I was asking. I see now in the chat that Caio has written. I don't think he has a microphone, so he's written his question in the chat, and he says that he researches biogas from sugarcane ethanol, and he would like you to comment on the production of biogas from vinasse, taking into consideration the comment regarding biogas and sustainable agriculture. So I wondered whether you, Bruce, you'd like to touch on the production of biogas from vinasse in terms of this model?
Well, there's of course I'm not an expert in biogas production. I'm not sure I'm an expert at anything. I try to learn a lot about a lot of things, but as my Brazilian friends know, I visit Brazil on a regular basis. Yes, biogas can be produced from the vinasse. Also, biogas is being produced increasingly in the United States, also as a part of ethanol production on the waste from ethanol manufacture. So I think biogas is already gaining a strong foothold in the ethanol, the biofuel ethanol industry. And what I would emphasize is the importance of getting the nutrients back onto the field as a part of the vinasse. Now, vinasse doesn't have the fiber content that, so there wouldn't be as much organic matter produced, but there is a lot of mineral nutrients in vinasse that need to go back on the fields, and I hope that that's being practiced. When I visited Brazil last and toured an ethanol facility, they do take the mineral from the ash resulting from combustion of bagasse to drive the system, and that goes back on the fields. But I hope and I believe that the biogas is also being used in the way that would allow you to recycle the nutrients. That makes a major improvement in the sustainability of the system. I hope that addresses the question.
I hope that Kai will be able to type something to respond to that. But in the meantime, I see that, yeah, he said, yes, thank you. Indeed, I see that David Chiaramonti has his hand raised. I wonder whether you wanted to ask a question.
Yeah, thank you, Natalia. Can you hear me? Okay, good. Hi, Bruce.
Yes,
very interesting presentation. David. Thank you very much. I got just a couple of questions, given also your wide experience in the broader field of biofuels. Regarding the biogas done right, we are working on the inclusion of thermochemical processes with this biochemical processing, like anaerobic digestion. Specifically, I think, and I would like to have your opinion on that, combining biochar and the liquid digestate together helps a lot to save leaching of nitrogen or release of N2O in the atmosphere. Of course, I refer to biochar from lignocellulosic residues, not from the digestate. just to clarify. That's one point. And the other point is on a broader context. I remember well your first article was not named Biogas Done Right, but it was named Biofuels Done Right, which personally I like very much because I think not only biofuels, but also biogas, but in general, biofuels, bioproducts, bioeconomy can be done right or not. So how would you translate this model to other bioenergy and bioeconomy chains? Do you see this possible, or do you see this approach restricted to the biogas due to the digestate availability, which is not always available in the other bioenergy chains?
Right. So Dave, that's a really good set of questions, and I'll try to answer them as directly and honestly as I can. I think we need to be really honest with ourselves in bioenergy. As you know, I've worked for 40 years in cellulosic ethanol, and that has largely not worked. And when you stand back and look at the reasons why it hasn't been widely adopted, I think there are two big ones stand out to me. We didn't solve the logistics problem. In other words, we don't know how to get cellulosic material to gather around and deliver to a plant. And also, it wasn't truly worth the farmer's while. It isn't really a central economic activity for farmers. So I would say that a biogas or any sort of bioenergy system, and let me have if I had the virtue of 15 years ago being wiser than I am now, what I think I would title this, instead of calling it Biofuels Done Right, I think I would title it something like Bioenergy Enabled Sustainable Agriculture. That gives us another acronym, BESA, which we already have too many acronyms, but Bioenergy Enabled Sustainable Agriculture. Because the bioenergy has to be there, or the bioproducts, or whatever value-added product you choose. It has to be there in order to allow the farms to make these changes in their practices that will make agriculture sustainable. So I'm very supportive of research and development activities that fit into that picture. But if we are, as bioenergy or bioeconomy enthusiasts, if we don't actually understand and deal with the fact that we have to deal with large-scale logistics here. We must, and that it has to be economically attractive for the farmer. We're simply doing, again, I don't mean to, I'm an academic, right? I don't mean to, but that's academic. It won't ever translate into the real world. And we can work on aspects of the system productively if the overall system makes both economic and environmental sense. And it must make sense for the farmers. And largely in the United States, that hasn't happened. For cellulosic ethanol. For the farmers in Italy who applied Biogas Done Right, it made sense. And so they adopted it very rapidly, and therefore you got this very rapid increase in sustainable bioenergy. And so any other application of this in the bioeconomy also has to also benefit the farmers substantially. So again, that's a long answer, but I hope it's clear. That's why I think now. I would call it, if I had it to do over again, I would call it Bioenergy Enabled Sustainable Agriculture, to keep the focus on agriculture.
Thank you, Bruce. Very, very good point. Just a final remark. There are several groups now working on pretreatment biomass also for lignocellulosic ethanol. I mean, something you published already long time ago about ammonia fiber explosion, and now there is some interest in going back to that times, just because the logistic problem is a major point. But I fully agree with you that farmers are and agriculture in general are where we have to put our attention. That's what we're doing with biochar and integrating with the anaerobic digestion. Thank you.
Sure, David. Thank you.
Thank you very much, David, for your question, and Bruce. We'll know what to call the webinar next time then. bioenergy-enabled sustainable agriculture. I can see that our colleague Bao from ECRE has his hand raised. Bao, would you like to ask a question? You have the floor.
Okay, good morning from ECRE in Praia, Cape Verde. And let's say we want to thank Bruce for the brilliant presentation. I'm here with my colleague Guy, who works also on clean cooking. We wanted to understand, because according to the presentation, Bruce, we have 55% biomethane content from the biogas produced. And then CO2 can also be removed from the gas that can be used in to power tractors and other diesel vehicles. Now, we wanted to know what is the benefit of removing the CO2 from the gas. As we know, biogas, as it is produced, can be used in diesel engines. And when the CO2 is also removed from the biogas, leaving with only biomethane, what is the added advantage? And what is the use for the CO2 that is removed? Thank you.
Okay, thank you for giving me a chance to respond to those two questions. The situations may be different in different parts of the world that have or do not have natural gas grid. But if you have an extensive natural gas grid, which we have in Europe, we have in Argentina and the United States, then when you remove the CO2 from the biogas, the biomethane, the renewable natural gas, is identical to pipeline natural gas. And so there are no issues, no problems in mixing it with the natural gas flowing through the pipeline. And that gives you some huge advantages in terms of distributing the product. Okay, so that's enormously important. In places of the world where the gas grid is not so developed, the natural gas grid, then that may not be so important. It may be more important to just use the biogas as it comes out, containing CO2. But also in the portion, so let me reflect on the CO2, and then I'm going to have to say goodbye here pretty soon. I have responsibilities with my church here in Salt Lake City that I'm obligated to take care of pretty soon. But let me just say about the CO2. There is a technology that's widely known, widely developed, whereby you can use electricity and take carbon dioxide and electrically reduce the carbon dioxide to methane. Okay, so you're adding hydrogen atoms, adding electrons to the CO2 to convert it to methane. And that is a very attractive, it's called power to gas, again, power to gas. And it means that sometimes you have very cheap electricity, which we have, in fact, now with solar and wind electricity. They're produced sometimes when there's very little demand for that electricity, so it's low cost. And if that excess electricity from solar and wind could be taken and converted into methane by, in essence, taking the reducing power of electricity to drive carbon dioxide to methane, then you simultaneously purify the gas. You make use of that carbon dioxide, improving its greenhouse gas benefits, and you get a material that once again is essentially identical to pipeline quality natural gas. This ought to help the spread of wind and solar electricity, where they're actually getting quite expensive now because of the mismatch in demand and supply. They're variable renewable energies. And we talk about that more in this paper that I've referred to a couple of times. But I think those are two issues. Make good use of the existing natural gas grid, places where they have a natural gas grid. Maybe you use the biogas as it is to produce electricity in places where the natural gas grid is already developed, and take the carbon dioxide in biogas and convert it to more biomethane using surplus electricity from solar or wind. Very attractive ideas as far as I'm concerned, and they make sense to me as an engineer.
Thank you, Bruce.
Okay,
I hope that he answers your question, but I thank you so much, Bruce, for giving so much of your time this morning. I know that you have to leave quite sharply at 7:15 for you. But I would just, as Global Bioenergy Partnership, we do have a very broad range of partners and observers, and so I'd really like just to be able to touch on what Christine has written in the chat here. I don't think he has a microphone, but he'd like you to talk about the applications in sub-Saharan Africa where farms are not so highly mechanized. And I'd just like you to quickly touch on this point before you go, if that's okay with you.
Sure. I'd like to know more about that so I could be more intelligent in my response. But here's what I understand. For one thing, the logistics systems are almost not developed at all. So that means that whatever energy or products you develop, you need to use locally. Also, that because of the distances in Africa between ports where petroleum products are brought in and the interior of the country where the petroleum products are needed, the transport costs really increase the delivery costs for sort of farming in central Uganda, for example. Using commercial diesel or gasoline is just simply out of reach. Energy, the actual value of energy, the value of commercial energy at that point is just enormous in terms of its importance to the farmer and also to the village, the area where it would be used. So what we need is more village or very small scale oriented biogas units that could operate on residues or perhaps even planted crops like the cactus, the Opuntia species, in those local areas to generate some electricity, some energy that would greatly improve the value of those people's lives. So we've done an estimate. The cost of electricity, or the cost of energy generally, and its ability to improve human livelihoods changes dramatically between the developed world and the less developed world. In terms of the ability of a unit of energy to meet human needs, increase life expectancy, increase health, educational opportunities, is about 10 times greater in the developing world than it is in the developed world. Energy is so important, and without abundant and sustainable energy, many of our fellow human beings throughout the world will never achieve the lifespans or the education levels that we would like them to be able to have because they have no access to energy. And so if I had another career, if I had another 40 years of life to work on it, I would be focusing on that problem. I would be focusing on how to deliver energy to rural communities throughout the less developed world. I think Biogas Done Right offers one way of doing that. I've begun to think about it. I expect to write more and to talk more about it eventually, but right now I don't know enough. That's what I've told you is what I know.
Thank you, Bruce,
and
and then we'll be looking out for your future publications on to give a more detailed answer on that. I mean, you actually touched on it before when you mentioned Italy, that the subsidies that were given in Italy for investing in these biogas systems greatly helped in the uptake. And I guess that this is a common theme, is that the financial aspects of investing in a biogas plant are extremely important, and it comes down to us promoting that and promoting awareness also in financial institutions to fund these kinds of projects that we know are really important for energy access. I'm sure you, yeah. So are there any more,
Yes.
I know that Bruce has to rush off, but if anyone else has any burning questions for him, I'm sure he'll be happy to answer them. I don't see any hands raised. So we've been in perfect time. And I'd like to really thank you all for your contributions today. and also obviously to Bruce for his extremely interesting presentation and also answering our questions afterwards as well. As I mentioned before, we have been recording the webinar and it will be available on our website, and we'll also make the presentation available as well for you all. So with that, I'd like to again thank you, Bruce, very much, and thank you all, and I wish you a very good day.
Thank you. Bye. Bye.
Thank you. Thank
Okay,
you very
bye
much.
everyone.